Today I'm going to continue where I left off on Monday. But before I got into that, I thought I would ask a few questions. So we're sort of 2/3 of the way through, or whatever, Idea League 1, week 1. And I'd like to have the opportunity for you to give us any corrections that you want. I mean, we're going to be correcting your papers, so you have homeworks to do for us, so you'll be delivering things back to us. But we're delivering, lectures and knowledge to you. So, for example, here's a question. Do you think, I mean, this is like for planning of the next 3 weeks in the course of the year at Chalmers and at ETH and so forth at Delft. Should we have exercise lessons during the week, would you think? Or do you think straight lecturing is working for you? Okay, so, well, kind of a mixed story. Would you like there to be sort of official office hours, so to speak? That is, kind of a time when you could privately talk to your professors about things, or do you think the public time is sufficient? So office hours? No. Okay, well, 1 or 2. Maybe I'll stop with the interaction for the moment. Of course, I'll start delivering information to you instead, the traditional thing. Actually, what we're told, the people in the Idea League have very different ideas, actually, about how schools should be run. I mean, they told us we should have a personal mentor who was with you all the time, who, as soon as the professor would leave the room, he would start asking you, well, how is it going, and, should they work more on your soft skills and things like that. And, well, we chose not to follow exactly the way they do things. This is obviously a kind of hard skills week, and that's the way we do things in physics. This is not business school where you have to learn how to entertain customers or something like that. Although it's not an insignificant skill in physics, I should say. Depending on where your career goes, you may indeed have to deal with customers of some company you're working with, or I mean, even professors have customers in a sense. Okay, let me stop all that. Okay, science. To turn the switch. So I'm going to So I return right back to this slide, and. Now, if you've been paying attention to what's developing in these schools, like what you'll have next month, for example, you may wonder why I should get up here and tell you much about superconducting qubits, because you'll have lectures from all the famous guys in Europe who are doing this. There will be Wallraff next month, and there will be De Carlo, and in the summer school in Sweden there will be Steve Gervin. So you'll get a very full dose of what's going on in superconducting qubits. Of course, there is a lot going on in that subject. There's a big meeting next week in the United States. I'm not going there, but it's the sort of big annual meeting of the Physical Society of the United States. And there are, well, I'm going to guess there are maybe 400 people there just to attend the sessions about superconducting qubits. So it's a very big subject. There are also hundreds of people working there to talk about spin qubits. So that's also not a negligible subject. So anyway, there's no experimental specialists here in Aachen who work in this field. However, we in the theory group actually have had a pretty long interest in superconducting qubits, and I thought I still had some kind of useful things to say that I don't think you'll hear from my colleagues at the other places, especially from the experimentalists. And Gervin's a big theorist in this subject, but I also think I will offer a somewhat different perspective than his. So here are some simple questions. I planned this lecture as sort of a hybrid of slides and Blackboard. So you'll be looking at both as the hour goes on. So these are the 2 questions that I'll pose, and this won't be strictly about superconductors. It's about the quantization of electric structures. So it's sort of this question of how does electrical engineering and quantum physics actually interface? How does it actually meet? What's at that actual meeting point? So circuits. So there's, these are some examples of electric circuits that I ended with the last time. the first question is a bit of a technical matter. That is, if I present you with a circuit, if I say that's a good model of the structure you're working on, what is the Hamiltonian of that? So that's, well, there are procedures for doing that, and I'll sort of sketch them, but I'm actually going to do that second, because I'm going to spend more time initially on the first question of what's the right circuit anyway. And I already, by pointing to these circuit elements, I was already implying that this, really didn't tell the whole story. That is, the model implied by this sketch, this discrete electric circuit, is certainly a model of a physical system which you can analyze mathematically and quantize and compute the quantum states of and compute the decoherence rates of if you have a little bit more in the model. But as I say here, is this really right? Or if I'd like to improve it, what's the right way to improve it? So that's what I'll spend time on now initially. So I will take you to some, actually this talk will also be a mix of quite current things. Okay, this is, I'm going to give you a little commentary about a paper that was published last year, well no, sorry, it's already 2 or 3 years ago, which gives one viewpoint on this and actually suggests a solution, or suggests a methodology for getting at the right circuit, at least for a kind of limited set of problems. I was going to make one comment about spin qubits. I mean, this is all about electric circuit qubits, and so it'll have to do with Josephson junctions. This all has application for spin qubits, but in a slightly less direct way. That the spin itself is not describable as an electric circuit. An electron in a quantum dot, its dynamics is not describable as a capacitor or inductor or whatever, or any two-terminal electric structure. But all the controlling structures around it can be, and especially there's a current trend which I think Lee van der Sijpen may lecture about, so that's another little addition to this, what's coming up in this subject. So for spin qubits, you can put them in a cavity also. So you can have structures which are like, well, what I put up a while ago, this electric strip line cavity, but with spins inside, with quantum dots inside. And so then the quantum mechanics of that structure, that cavity structure, is very much an electrical problem and amenable to, well, descriptions in terms of circuits and then quantization using circuit quantization techniques. Okay, so let me again state the problem that, well, these circuits, or at least this is a schematic of a single qubit structure in this world of superconducting qubits. So stripped down to its bare essentials, it's just this Josephson junction, and I'll come back a little bit to the story of what is a Josephson junction. I won't get too deeply into it in this lecture, but it can be thought of actually as just a particular kind of nonlinear inductor. So it also is to some extent a familiar object in the electrical world. And then it's connected up to some other thing which we've been wanting to describe as well, as some LC circuit, and you're capacitively coupled to that. But this paper invited one to take a more general view of that this, going from the ends of these wires to the interior of this cavity is, well, it says a black box. That is, it simply has some kind of response. It's some kind of electric object, but perhaps you would rather not ahead of time want to assume what it is. That is, you'd like to go through a rigorous procedure to determine what it is, rather than just assert that it behaves like an LC circuit. Now, I don't want to point to these pictures so much. That has to do with another point. But it's this little story that is, so they introduced a suggestion, which is based partially on a rigorous idea, it turns out, which is that this cavity, well, let me state a little bit more about what you should think about a cavity. So you have, a structure as Josephson junction. Now, the point is that this is a structure which, well, it carries electric current. and there's some voltage. Actually, more usually we focus on the so-called, well, on the difference of superconducting phases from one side of this junction to another, but that phase difference has the property that its time derivative is proportional to the voltage. So I often slip back and forth between this sort of purely electrical language where I talk about voltages and currents and this sort of more physics language where I talk about phases and currents. But in fact, the two are closely related because of this time derivative relation. This is one of Josephson's laws about electric circuits. So these wires come out, and I mean, they correspond to real physical things in the experiments that I reviewed on Monday. And then they enter some structure. And the point is that this is a structure which, well, if there's a current going into it, it is itself a two-terminal object, even though it's composed of some large structure. You know, it is not in its interior a discrete object, you know, one electric component, but nevertheless it's fully describable. Well, what assumptions do you make? You assume it's linear. You assume it has a linear response, and you assume it's well, passive. Passive meaning, you know, they're not batteries. It's a, you know, it's a metal structure which is supposed to have resonant modes. So it should be passive. I may come to, there are a few more things that actually constitute a rigorous mathematical, you know, set of statements about what this box consists of. But it is a box, and I could even erase this, or I think of these as two separate sides of the story, that there is if there's a current going in and out of this box, then there is indeed also a voltage of the box. And we define now these are both in general time dependent, and the relation is not necessarily instantaneous in time, but in the frequency domain, what we say is that of course, the voltage at some frequency is indeed a linear function of the current in at that frequency, and the relation going via the impedance function. And of course, if the interior of this box really consists of, let's say, a capacitor and then an inductor and another capacitor, if that's the black box, then it's an elementary job to actually compute. I mean, you learned maybe even in high school how to compute this impedance function for this little assembly of circuit elements. But that's not necessarily what this box really does. I mean, in the experiment that I showed a minute ago, I know I'm going to have trouble going back to this, but let me do that for the moment. Oops, yeah, oops, yeah. Okay, now believe it or not, I am actually back to where I was. There, okay. See, it's not only our quantum computers that don't work. You know, here's this, now one can ask where are these terminals on this picture? And here it's, well, two places in this green structure looking outward, so to speak, from the qubit. You have this whole surrounding electric structure. Now, sorry, this is going to go blank again, but don't panic, though. I'm telling myself, actually, not to panic, of course. Because I wanted to come again to this picture and say that this was offered in this paper by the Yale group a few years ago as sort of the solution, and it was based on on old ideas, even older. This is a very old, famous text in microwave theory, but it actually goes back even longer than that. So it turns out there is a theorem that, but which has a big proviso that concerning this black box. If the black box is lossless, Now, okay, lossless means capacitors and inductors and things like that, but not resistors. If it's lossless, then any black box response has this so-called Foster form, which is in fact, in general, what you see there, except without the resistors. So it's a sequence of oscillators, of LC circuit sections. The number not being specified. Maybe I can bring this back over to here. So in other words, this is the black box. So that's a pretty powerful statement in the sense that these structures, I'm not going to try that again, but if you have a cavity, so some strip line cavity, has some conductor here and a thinner conductor and then a thick conductor, and we're sort of probing its current voltage relations by some little Josephson Junction structure, that it's perhaps surprising that this whole extended structure is representable by, now I should say, a sort of innumerable number of these. That is, you can ask how many stages of these do you actually need to represent the lossless response of some extended electric structure, meaning, it's a structure that in which Maxwell's equations are obeyed, and it has some conductors, lossless conductors, electric conductors, and lossless dielectrics. And the idea is that, that it will itself have eigenmodes. Oh, it's assumed indeed that this is a closed system, so that's a limitation related to its losslessness. So you get to, in a sense, put this in a big box. And then this is sort of a statement about the wave equation, namely that it does have eigenmodes, and that the response of those eigenmodes to an external probe, electrical probe, is just as if it were a series of LC resonators. I might mention, it's perhaps useful, what Foster showed is that this also works in a kind of dual form. That is, there's also an equivalent representation in this, as I say, in a sort of network sense or a graph sense, dual form. These are two different ways of representing a set of eigenmodes, basically, of an electrical system. So this is the Foster form. This was actually a theorem in 1924. So as I promised, this sort of casts far back. And so in this work, at Yale, they did just one thing. I mean, lossless is fine, but then you can write it down, but it doesn't actually answer a lot of the important questions about a circuit, like what decoherence does it suffer from? That is, this is jumping sort of into the question of how you quantize these, but I can promise you, or what I will show you more explicitly near the end of this lecture, is that if you have a circuit of any arrangement with inductors and capacitors and Josephson junctions alone, that there is in fact a Hamiltonian for that, and there is therefore a Schrödinger equation for that, and it has eigenlevels. But we know that's not the only thing we're interested in physical qubits. Like, we'd like to ask how decohering, what's the decoherence properties of it? What's the decoherence time? And such a thing is absent from a model like this. And so we'd like to have more information, and in fact, it's very valuable to be able to represent laws. And I'm still talking, and for a lot of this lecture, it's rather like Renner's lecture, I will be talking classical physics, but there will in the end be a simple prescription for how I go over to, or a simple set of prescriptions for how I go over to a quantum description, including the description of the resistors. So I'll be getting to that, but I view it as a completely legitimate thing to ask, by experimental probing or by running some simulation using the Maxwell equations, to extract resistances, to announce this circuit is lossy and it has a certain resistance, and in fact, and then to carry that over and to invoke that resistance as a source of decoherence. So in fact, that is precisely the procedure involved in describing what's called the Purcell effect. Purcell effect is basically a T1 mechanism. It's an energy loss mechanism for a qubit related to the presence of a resistor in an electric structure. Okay, but I'm pursuing a little bit of a different program here. I'm asking, I mean, it's possible to have circuits with resistors here, but I want to ask it the other way around. If I have an actual electromagnetic structure, which has now lossy conductors, so therefore these can't be, this Foster form is not strictly applicable because it's not a lossless system anymore. I mean, I have to use resistors somewhere to represent its response. And as you see, what's done, well, what was recommended, in fact, by the inside this book, but I don't think it's unique to this old book, is put the resistors here. It sort of comes from a natural physics thinking that each of these are some kind of pole in a response, a pole in this impedance response. And this is just giving each pole a lifetime, or giving each pole an imaginary part, giving it a lossy part. But I was surprised when I saw this paper, and then they developed some interesting physical theory of cavities based on this, which they also referred to as Foster form. But as we say, Foster would have turned over, or probably did turn over in his grave when he heard that this was his form, because he proved nothing about this, about whether this is in fact a good way in electrical engineering to state, to give an accurate model of the lossiness of a distributed structure. And in fact, it's even worse than that. It was known shortly after his theorem was proved that this was even false. So this model is wrong, actually. I mean, the green part of the model is wrong. This is not an accurate way of describing the response of an electrical system. And there was some period where I think the problem was open. That is, it was really an open question whether the lossiness of a structure described by Maxwell's equations and with lossy conductors had a discrete electric circuit model that was in any way or in some way related to this canonical Foster form. So let me give you a little story about that, because this problem was solved. And the answer is there is, in fact, a canonical circuit model, which is not a simple generalization of the Foster form, it turns out. Now, I know, in fact, that a few of you, well, I've spoken to one of you in particular, has an electrical engineering background. So it would be fair to ask him, and probably unfair to ask the others. Sorry, I'm jumping to something else. The solution was given in this PhD thesis, actually. So those of you who say, oh, I'm doing my PhD, but surely I won't have any significant impact to me with my little PhD. But this was actually a quite extraordinary paper, and was well known for decades, I would say, in electrical engineering, but I don't think is known so well anymore. So has anyone ever heard of the Brune technique? I'm looking at my electrical engineering, you don't know it, no. No, I know, I mean, I attended lectures in electrical engineering in the 1970s, and this was still somewhat known at that time, but it was not a very popular subject in electric theory at that time. But it's still, well, I think it's undergoing a little bit of a revival because of problems like this, because of sort of a new rigorous interest in problems in electric theory. Now, I'm not sure that, okay, the title doesn't help too much. But the point is that Brune found an algorithm, which is, he showed, he proved there is in fact another canonical form, not this one, but something a little more related to this, but as you'll see, it's a non-trivial extension of this model. But he found an algorithm for constructively determining a circuit model that would accurately represent loss. And then we recently figured out how to quantize the Brune construction. So I'll tell you that, and I realize that will probably be most of the hour, but I have a little more material just in case. So let me tell the story this way, and okay, this screen will go blank again, but don't panic. What I wanted to show you was some real data. Let's see, which way do I want to do it this way? Well, I'll show it with some extras here. This also shows my collaborators on this, so including those of you locally, of course, know my PhD student, Firat, who is just finishing his PhD next month, I should say. So here's an example of, quote, reality for us. So this is a particular sketch as rendered in a high-frequency simulator of a cavity structure, actually the interior of the cavity, and these are the walls of the cavity. And then there are some access ports, so they're actually models of the cables that come in and out, with eventually coaxial cables going off from here. And what you can't exactly see is there's also a small chip mounted in the center of this cavity. And in the chip, or on the chip, is evaporated some metal structures, and somewhere right in the middle is a Josephson junction. So that's sort of the one half of this story. That is, there's a structure which is physically very small, is not linear. So remember, I did mention the main consideration about this. The rest of the world is by hypothesis linear, but this is not. In other words, it does not have a linear IV relationship or phi I relationship, and that's essential to making this a qubit. But the rest of the world is considered to be, and is indeed constructed to be, linear, with a cavity with superconducting walls. But actually, such cavities are also made with copper, so superconductivity is not absolutely necessary for this. But this is, in fact, a simulation which tells something about, mode structure that appears, if you excite this cavity at some frequency or near some resonant frequency, what eigenstructure do you see? And this has, this has index or quantum number 3 in this direction. As you see, it has three antinodes in this direction. But I thought I'd show this just to show this is also another typical output of a simulator like this. And this, can't quite read this, but at least for the discussion that I'll be giving you, we'll be talking about, say, the real part of this impedance function. This impedance function is, of course, a complex quantity. And since this is lossless, the real part is non-zero, and it has lots and lots of structure. Now, it has structure. It has strong peaks at places which are near resonances, near eigenmode resonances of a sort of hypothetical lossless structure that it corresponds to. In fact, we will be considering structures whose loss is low. But I mean, that's the whole point in superconductors. I'm sorry. Well, for qubit systems in particular, is to have low loss, and therefore not very rapid T1 decay. But still, absolutely non-zero. Actually, in the cases we're considering, most of the loss comes from the fact that this just happens to be another rendering of the same thing. Most of the loss comes from the fact that this is connected to the outside world, not very strongly, but loss occurs through basically disappearance of signal. I mean, if you think of AC signals, they disappear out into this sort of infinitely long cable that's assumed here. But even still, the lossiness of this structure is not very large. So let me give you an idea of what Brun discovered, and it was admired for a long time as being, a rather daring deduction of, because I'll show you, it's not, it looks like it's going to fail, in fact. So, let me just sketch. This gives the sort of core, oh, sorry, I didn't put it up there yet. This gives the core of this Brun construction, but I want to talk through, what's apparently lunatic about it, what would suggest that it really doesn't work, and then explain why it does in fact work. So the procedure goes as follows, and I'll use this sketch. what you saw from the simulator, from the high-frequency simulator, was this on a log scale. But let me assume that it is, in fact, on a linear scale. That helps emphasize the point that it is, in fact, always positive at all frequencies. Positive, or, well, it can be 0 if the system is lossless, but is generically a positive number at all frequencies. It absolutely cannot be a negative number. That would correspond to negative resistors, basically. So it would be an unphysical system. It would be a system which was emitting energy rather than absorbing energy, so violating the second law, whatever you want to say. So it's some positive function, and this is just by sketch. And so Brune's algorithm is to say, first of all, well, there's something called a Foster preamble. So you can have a system, but very non-generically, that does actually have a lossless resonance. And so you take it out initially. So you do a little bit of this initially, and then you're left with, the rest has loss, so it has no place where this goes to 0, for example. And so you you find the minimum point of this frequency-dependent function, and you call this scale is real part of impedance, so it's in ohms. So this is some resistance, some number of ohms, and so that's what's called R1, and you just stick that in. So you're trying to make an element-by-element model of the response. So you've, so to speak, taken away a resistance. So when you look at the response, so you're modeling, the black box starts here, but now you've taken away one resistor. Now you're trying to look at what's still left to the right. And you've now got this very non-generic response where the real part really is 0 at that one specific point. So I could redraw this, but in other words, the real part of the impedance is just shifted down by R. So now this is a rather special frequency. Call it omega. Does it have a name here? Well, I'll call it omega 2. Now, there's also an imaginary part of the impedance, IMZ. Well, what comment shall I make? It's the Kramers-Kronig transform. I mean, these are Kramers-Kronig pairs. That's the sort of condensed matter physics language for it, or they're Hilbert transform pairs. That's one aspect of this being a causal system. That means some things about what this looks. It definitely has some. It has both positive and negative responses that are correlated. This is a very, very poor sketch of the Hilbert transform of this. But I should emphasize, though, that at this frequency omega 2, this has some non-zero value. So I will call it, actually it's typical to call it x. And now recall that an element L1 has an impedance. The impedance of such a thing is I times omega times L1. So this is a pure imaginary thing. And so I can equate this to x at this frequency omega, x being in a pure imaginary, as you see, or I could put Ix here. So L1 is x over omega 2. So that's the next step in the algorithm, is to take out both, first the real part, then the imaginary part. Now, it turns out there's a problem, which is that this, you might say, has a 50-50 chance of being positive or negative. So one would be tempted to stop to say this is not a smart procedure if L1 turns out to be negative. But Brune's cleverness was to keep going a little further, to say temporarily, I know I can't have negative inductors. That also, I guess, in a more subtle way violates the second law. But I'm going to proceed anyway, just see where I can get to. Now, by doing that, what he's done is he's subtracted away not a constant, but just a linear function. So the remaining impedance is the white sketch minus the green curve. So that's the impedance at this point. But now this Z has a real zero. So observation, going over here. So the Z now has a zero at omega 1. I'm sorry, omega 2, I called it. So both its real and imaginary part have been set to 0. Now that means the 1 over z, the admittance, so y 1 over z, has a pole. And so that's actually now back to the sort of Foster story. And you extract a pole, is what we say. This is a way of taking out a pole in 1 over z. So that makes reference to this Foster form. So you get an LC circuit, and there are straightforward ways of calculating the parameter values of these two things. And then you're left with something that, may at this point be non-causal, but I'll come back to that in a moment. But it anyway is some new function, and it just has one property that, if you look at what's left, the mz that's left, it'll have some structure, whatever, but it'll be at plus infinity, it will look like an inductive. That is, if you have, if you have any circuit with an inductance in series, at high frequency, it will eventually dominate the impedance. It'll go, it's this omega L. So eventually, it'll go like some omega L, in this case, omega L3. So the final step is to, of this algorithm, is to identify that L3 and take it out. So subtract it away. Now, it sounds like this couldn't possibly, be physically meaningful, except for two pieces of algebra, which comes out from a longer derivation than I'm, of course, going to do at this moment. But the facts to be featured are this, that first of all, it turns out this final inductor that's extracted has a simple relationship to the first two that were extracted. Here's this L1, L2. There was also a capacitor C2 that's not shown here. So it's a simple algebraic relationship. It's also a crazy one in the sense it has this minus sign. So it says during this procedure, it was guaranteed that either L1 or L3 turned out to be negative. So this T of inductors is guaranteed to have one negative inductor. But he observed, or the miracle that occurs, though, is that the three-terminal response of this thing, which contains this unphysical inductor, is equivalent to a completely physical three-terminal response of two coupled coils, with some formulas given here, with only one special feature, which is that the mutual inductance turns out to be maximal. Now, I'm not sure, okay, this is probably none of you are really so current on your transformer theory, but there is a physical limit. If you have two inductors, then you can have a mutual inductance, which has to do with the fact that the magnetic flux that's produced by a current here also passes through the other coil. But there's an upper limit, which is again basically a second law, or maybe it's even a first law. I mean, this will be an energy generating device if m exceeds some value, and the value that it may not exceed is the geometric mean, the square root of L11 times L22. And it turns out for this construction, it is exactly at that limit. So it's exactly at the upper limit that's permitted physically, but it is still, indeed a permissible value. So by doing this substitution, this negative component value is in fact cured. And the other thing that turns out to be true but which takes a real analysis of this whole construction, is that so now you're left with a Z2 which is itself also physical, but reduced in degree. That is, and that has to do with the fact that as you can imagine, this Z is itself some rational function of, well, this is using this Laplace notation x, but it's some rational function of frequency with some degree of the numerator and the denominator. And the degree of Z2 is guaranteed to be reduced compared with the degree of the original Z. And so this is guaranteed to be a procedure that will come to an end, in fact. So the algorithm is to repeat. You do the whole story again, and a certain number of repetitions are guaranteed to be able to reproduce, well, in the same way, no, I guess maybe I didn't even say it, in the same way that the number of Foster stages is innumerable. That is, if you, say, take a particular range of frequency, which might be very large, and you say, I want to represent the response in that whole finite range of frequency, then only a finite number of stages is necessary. And the same is true for this, but now accurate and successful way of writing a circuit. So, so what we discovered? No, we rediscovered by reading, the texts from many decades ago, is that there is in fact this discrete representation, which is, accurate. I mean, as accurate as you would care for it to be. So that's the right circuit, is the first answer. The Brun circuit is the right circuit, that it will indeed describe the classical response, describe the classical dynamics of any arbitrary cavity. So let me illustrate this by going to an example. So I've shown you, well, no, I didn't show you this already, but if you, one of the various things that we simulated has a response. Let's see which one I want to show you. The darker curve, the dark blue, is some real data. The axis is the real part of Z, again, the imaginary part not shown. But this is a real cavity that, or no, I mean, it's a model of a real cavity. It's a model of a high-frequency simulator model of a cavity that people have really put, or the IBM group has really put a qubit in and used it in this Jaynes-Cummings fashion. What that meant was that it focused on, or it pretended, or the Jaynes-Cummings view pretends that this cavity has one mode of resonance. Here's a notation which which I had on some earlier plots, but it doesn't matter if you don't know this, but if you happen to know it, it is a TE mode of the cavity with these quantum numbers. This 101 refers to a number of modes or number of wavelengths or half wavelengths in the three different directions of a rectangular cavity. So here's, as seen at the terminals of the qubit is sort of a probe right in the middle of the cavity. So it sees this 101 mode. It doesn't see the 102 because the 102 mode has a node, has a 0 basically, where the qubit is. So there's no response there. And then it strongly sees the next mode, 103. These are gigahertz units, so this is over quite a wide range of frequencies, but a perfectly accessible range of frequencies. So there's some other funny stuff which frankly I don't understand. There's a tiny little resonance. I mean, there is a resonance with a very small coupling to the qubit. And I don't know what this is. I don't think we were able to diagnose it. And there's also some funny interference between the lossy part of the impedance, sort of in between here. It's indicative of some kind of interference effect, basically, that there's a big dip, not going to 0, but see, this is a log scale, so this impedance gets extraordinarily low at some point in between here. Now, the kind of orange curve is the best you can do with this sort of fake Foster form. So if you say, well, this can't be too wrong, I'll put these resistors here and I'll try to do as good a job as possible. And of course, with a model like this, it's actually very easy to find the parameters. You choose the LC resonance frequency to coincide with these two, and this is a two-mode or a two-stage fit, and then you put in resistors which try to match the shape of the peaks pretty well. And then it does quite a bad job of representing the details in this region. And there's no way to improve it. I mean, that's as good as it does, and adding any further stages does not do anything to improve the details of the response of this cavity in this region in between the two resonances. So what I'll show you is the sort of behavior of this Brun circuit in achieving, in representing this particular response. So, and the way I've got it in these next few slides is to just show you what you get. Well, I don't have a sketch of the Brun circuit, but let me just bring it up for a moment. Finally, there's a full Brun circuit. I guess it's this one, which is one stage after another. This already, okay, as you see, this has to do with how you quantize this circuit. Now, I'll get to that in the coming minutes. But first I wanted to show you, if you look into this black box, you can ask, what does it look like after the first stage? And then what does it look like after the second stage? So after the first stage, it's, when I say first stage, I just define it as being the first resistor. So that's not a very good representation of the response, of course. Then you go the next stage, and you've got one resonance. Actually, this scheme puts it neither at the one big resonance or the other, but in some apparently random place in between. So this is also the first stage model. Again, I can't point to this, but the first Brun stage does a very poor job of representing this data. I mean, it can't do very well because it has only one resonance. When you put in the next stage, it already does somewhat better. It now finally, it has zoomed in on this, or now it is right on with this 101 resonance. This 103 resonance, it's only, somewhere close, but it's already got this dip, though. It knows something about this phono interference, or well, there is some kind of interference phenomenon between these two modes. Next stage, it's got this frequency pretty much right on, and it's got some kind of approximation to this structure. I didn't say anything about it, but it also, it's getting the right upswing of the impedance here, and it's not doing particularly well here, but okay, in next stage, I think we have, there's still quite a few stages to go, but you'll see they only involve very fine adjustments, basically. And the further you go, the more fine details this manages to match. See, finally at the sixth stage, it decided, okay, I better work on putting in a tiny resonance there, because it's in the response. So it did it. I mean, I can go through descriptions of why it's so small, and it's seen by the qubit only through a very long filter, in a sense. I mean, that does not say what it is physically. And then finally, let's go, we're near the end, but going from 7 to 8 does a dramatically improved thing here. So boom. I'm saying this is a, quote, smart algorithm. Of course, it's just an algorithm. It's just running through some formulas and computing some component values. But it is kind of mysterious how it sort of sharpens up, successively sharpens up the description of this circuit. Now, it turns out it never quite gets this dip as deep as in the data. And what I don't know is whether it is, in a sense, critiquing the data. It's saying, well, that data is not really physical. That is, it's going too deep to be a genuine physical response, and it was really some problem with the simulator. Because remember, these are very tiny resistances. These are 100 micro ohms at this point, the scale here. And the max is up here at 1,000. So it's dealing with a very large dynamic range of impedances. So the other problem, that's in fact the full model. So the other problem is although it's very accurate, it's quite a large model. That is, as you'll see, if you say, what's the Schrödinger equation that corresponds to a 9-stage Brun circuit, it's a pretty big, ugly beast. So it's something that you need to have some intelligence to deal with anyway. It turns out to be basically like a Schrödinger equation in a very strange 9-dimensional space. With huge dynamic range between the different dimensions. But let me go on to that a little bit. So, and I'll take this. This is now a bit of a transition in this lecture because that completes our, up to the minute work on what's the right circuit. Although, as I said, it was basically a matter of accurately learning what was done 80 years ago. And but now I'll tell you about how you quantize these things. Yeah.
I have a question regarding the plot on the previous slide.
Okay.
Can you tell me the order of the Foster model?
The
Just three orders of Foster and a lossy Foster model. What's the order?
Oh, a good question. I think this is only a second or third order fit with lossy Foster. Yeah. Okay. I mean, it has to be admitted we didn't go. Oh no, I'm sorry. It's at least. It's obviously, okay, it's at least 3. I'm stopping to think it's, I'm rereading in my mind the pages in the thesis about this. It's something larger, but not quite as large as 9. Let's say it that way, because in fact, there are other poles. There are a few poles down here, which you don't see. And I think there's also one pole up here that you don't see in this range, and it went ahead and fit those, but it can't, some of them it actually couldn't fit because, well, a highly technical reason. The residues were complex or something, and the Foster model can't deal with that at all. Okay, so I mean, you could indeed say, well, was it really a fair comparison? But what I know is certainly true is no matter what order lossy Foster you do, you cannot fix this problem. It seems like it is really inaccessible to lossy Foster. Yeah.
My question just been more of a historical one, but I'm curious as to why what seems like such a good model was forgotten.
Well, I can tell you why it's forgotten in electrical engineering, because electrical engineering, well, linear analog systems is very, very obsolete it's very untrendy in electrical engineering to concern yourself with linear analog systems. I think it's actually only in this field of low temperature electronics that there's actually sort of a reblossoming of interest in the sort of fundamental features of linear analog systems. As far as I can tell, it was basically never known to physicists, and I don't know why it never made that crossover. Like in this famous book, well, I've mentioned it a few times, this Dickey, Montgomery, Purcell book, which is considered a great, text and it's actually a chapter book, so each chapter is written by somebody else, but it's still used today. It was definitely a product of physics, and there's no word of Brun in there, and not even a sign that Brun was known to any of those people. Even though, if you look at electrical texts, or I had some pictures of the cover titles of those because they're not easy to find, but once you find them, there were actually plenty of books for decades and decades in electrical engineering that went to the trouble of teaching about this construction. But they're quite rare now. There are very few books now that bother teaching this construction. So, no, that was an interesting aspect of it, to indeed reconstruct the history of why this thing got so thoroughly buried. Now, so I will make some comments about how you quantize this. So first, a few sort of general comments. Recall, there's a resistor for each stage. There's also finally a resistor that terminates this. Now, forgive me, this is first of all in a very hard to see color, but in a sense the reason for that is we did some trickery in applying some formalism where we first pretended it's a capacitor. But it's all mostly technical, so I don't want to actually spend so much time telling you about that story. But anyway, there are certainly resistors here. Actually, it's interesting. Okay, I was going to leave the subject of this electrical thing, but there's one other aspect of it that I think is worth mentioning that is really a physical thing. Oh, and do I have it here? Yes. I mean, usually it's rather boring to look at a table of numbers, but let me just emphasize one thing. So, I mean, okay, we extracted these parameters. Now, this is supposed to be for a cavity that really functions with a qubit, that really realizes a Jaynes-Cummings model. Now, you can imagine you can't survive much resistance in that case. And indeed, the first stage resistance is very tiny, 50 microohms. So, but that's maybe worth thinking about. That is indeed a scale of resistance that's characteristic of sort of a state-of-the-art superconducting qubit. So it does really have that much resistance, which is really very tiny, but it's not lossless. It's not zero resistance. The second stage resistor is already 3 orders of magnitude higher, strangely enough. And the only explanation I can give is that, by contrast, is not directly connected to the qubit. It's not, the Johnson noise from this first resistor, from R1, is sent right into the Josephson junction. So it's completely destructive as far as the coherence is concerned. The next one is already only seen through this LC filter, so to speak. So even though it's more resistive, and we checked this actually, I mean, this is jumping ahead, but we can actually one by one enumerate how much each of these resistors, these abstract resistors, contribute to T1. So how much each of them contribute to relaxation. And for the first few, they're about comparable, even though the component values change enormously. So third stage resistor is 180 ohms. Next one is 17 kiloohms. So there's really no idea of, well, all the resistors are small. Actually, they ramp up, and they continue going up. And then the terminal one is almost a gigohm. Although it's actually then in a position where an open circuit is actually a good lossless situation. So somewhere through here, the mindset is better to transition and say, well, that's almost like an open circuit, which is also a lossless condition. But there's no real sharp break, in fact, between the sort of lossless because zero resistance to lossless because it's infinite resistance. So we're still sorting these things out. I mean, I think we're trying to use this, actually build a sort of physical intuition based on this model. I mean, with the understanding that these are kind of imaginary. I mean, there's not any place in the cavity. You can't point to that conductor and say, aha, there's R1. It's itself a very distributed idea. But it's, in a sense like a eigenmode analysis, but for resistances, for losses. Okay, so now I was going to, I explained that I would spend some of the lecture now really probably the rest of the time that we have energy for talking about, so we've got a circuit and we really trust it, and what's its Hamiltonian? And so the reason I got off on those side remarks is that, of course, the resistors, you should be able to imagine that I can't write a Hamiltonian for the resistor. That's sort of a well-known idea, that a resistor is an irreversible, or it causes irreversible operations. Their heat is generated, it causes loss. So there's not any simple degree of freedom associated with the resistor that should appear in a Hamiltonian. However, it can appear in a master equation. And that's going to be the structure of this, that we will do this in 2 stages. There will be a Hamiltonian of the system, of the lossless system now, but not really the Foster lossless system, but the lossless system corresponding to this with the resistors temporarily ignored. So there will be a Hamiltonian of this, and then there will be and that will really give you a Schrödinger equation for the dynamics ignoring the resistances, and then you will have terms in the time evolution of the density operator, in other words, a master equation, which will represent the contributions to the dynamics from these resistors. And what it means is that you introduce actually an environment that represents the dynamics that mimics the dynamics of the lossy dynamics of the resistor. And that's actually has been a well-established technique. I mean, we just adopted ideas that were introduced by Caldera and Leggett, who gave quite a general prescription for how to do such a thing, for how to do this open system quantum description of a resistor. So the first task is, how do you make a Hamiltonian of this thing, this structure with inductors and capacitors and Josephson junctions, and also mutually coupled inductor pairs, even maximally mutually inductance coupled pairs. I want to give you at least a few summary remarks about this. This is itself a big subject of how you systematically write down circuit Hamiltonians. There's a sort of simple way of viewing it, which is you say, well, a Hamiltonian, you can also use Lagrangians, it turns out, but you need to, I mean, a Hamiltonian is a description of energy storage, and you usually say, well, there's kinetic energy and potential energy in a mechanical system. But here you would say the words electric stored energy and magnetic stored energy. And then you would associate inductors, the magnetic energy stored in the inductors with potential energy, and the electric energy stored in capacitors as a kind of potential energy. And that's, as a first sentence, the right idea. But it's not nearly so simple as that. That is, you cannot simply write a set of terms, one term for each capacitor and one term for each inductor, and be done with the job. The main problem, it turns out to be that an electric circuit, or a graph of an electric circuit, has many linear constraints. There are Kirchhoff laws, so like the voltage around this loop, the sum of voltages around a loop is zero, right? The Kirchhoff's voltage law, or the currents flowing in and out of each node is zero. Each of those is a linear constraint among the circuit variables. So it's quite some job just to determine a set of independent variables that do not have any constraints between them, that can describe all the dynamics of a circuit. So I mentioned, there's something called a tree construction. So I think I have some other slides. Well, maybe I'll continue along the lines here, that the way you proceed in this job is you consider this as a graph, as a mathematical graph with nodes and edges. And it turns out the procedure for quantization is to identify a so-called spanning tree of the graph, which is a subset of the graph which has no loops. And that's a first step in isolating and identifying the independent variables of the problem. So I thought I'd spend a little time reviewing that. It goes back to work that I did with collaborators about 10 years ago, but I think we developed it quite carefully, so I'll just give you 5 minutes of thoughts about it. But let me first give you the answer, though, because you may as well at least have a sense of what it looks like. So the answer can be written in terms of, you have to make a choice of what circuit variables you focus on. And there's some freedom even in that. You can focus on voltages or currents as independent variables. And you can quantize either way. Or you can focus on other things like the charge on the capacitors or the magnetic flux of the inductors. And so what we do here is the final thing. So there is finally again, just of this lossless part, there's a Hamiltonian, and it has parts that, for those of you who have even this fairly small familiarity with superconducting qubits, has the sort of basic structure. So it has a term which is like q squared over c, q squared over 2c. So it's, in a conceptual sense, standing in for the electric stored energies in the capacitors. However, this c, it's matrix valued c. Let me come to that in a moment. There is a potential energy, so a function of these fluxes, these words say that they are themselves not exactly the physical magnetic fluxes of each inductor, but rather specific linear combinations of neighboring fluxes that stand in this equation. So you get, first of all, one single isolated term that is the contribution to the energy from this nonlinear element. So it has this cosine dependence on a kind of collective variable that is summed over all the fluxes in this chain. Actually, that was only in one particular, well, let me pause here. I think I meant to correct this because in fact, within one representation, this is a variable that's only, is basically just the flux variable or the phase variable of the junction itself as an independent variable. Sorry, but anyway, then there are additional quadratic terms. These are like harmonic oscillator type terms involving these variables. And what's a little illuminating is to see, so these matrices, there's a capacitance matrix, and there's this, which is basically an inverse inductance matrix. That is, this is like 1 over 2L phi squared, which is one of the ways of writing in elementary, using elementary considerations, what's the stored energy, stored magnetic energy in an inductor. However, these are both non-trivial matrices, but it turns out they're kind of tridiagonal matrices. So this is the capacitance matrix, and it has a relatively simple, oh, sorry, this got cut off, but it has a relation, I mean, the values of the capacitance that appear here are the physical capacitance is modified by these things, T's, which are the so-called turns ratios of these transformers. So there's an explicit formula for this sort of diagonal capacitance matrix, and then there's a similarly not quite diagonal, but again tridiagonal inverse inductance matrix also involving these turns ratios. So you can explicitly construct the Hamiltonian, and it's basically the Hamiltonian of, if you think in terms of a condensed matter physics problem, it's like a set of coupled modes or coupled bosons, basically coupled bosonic modes, which are coupled in a chain-like fashion, so somewhat reflecting the chain-like structure of the system itself. But it's different. In Foster, these are already pure, you can do a similar quantization of Foster, and this gives you purely diagonal things. These are already decoupled in a quantum mechanical sense. With Brun, they're coupled sort of nearest neighbor. So these modes are not yet the eigenmodes of the system. Maybe I'll mention, well, you can also take account of the effect of the resistors, but this again, well, I can't in 10 minutes explain this so well, but there's also a prescription which goes all the way to a prediction for the T1 rate, so 1 over the T1 lifetime, contributed by the jth resistor. And it's something that involves, well, simple factors, a thermal factor, but then a so-called density of states, and here's where you see the resistors appear in this expression for this spectral function, but also capacitances. And then there's a particular coupling vector which tells you basically this resistor J, how many of the modes along this chain does it actually couple to? It turns out it couples to all the ones that are downstream to it, according to this. So this vector, this m bar vector, is 0 for the first J stages, or J minus 1 stages, then there's some particular non-zero coefficient for all the rest. And finally, it's some transition matrix element between the excited state and the ground state. Now, actually, computing this matrix element involves a full solution of the Schrödinger equation. But the fact that it is this matrix element can be computed basically from circuit theory. Now, let me jump a little bit, but I realize I can't say very much about the rest of the story. But let me, as I say, at least give you a little flavor of this subject. So this goes back, as I said, to a more general setting. I mean, suppose you're told this is your qubit. I don't know why you would be told this is your qubit, but it's just some network some arbitrary network of maybe more than one Josephson junction and some inductors and capacitors in funny places, and also other kinds of nonlinear inductors, and then finally some resistors someplace. There is a formalism in which you first, as I say, take, this was actually a particular sort of realistic qubit that was being studied at IBM at that time, and find a subset of this graph which has no loops, and then the backbone of this basically specifies which can be the independent degrees of freedom. And then it turns out that, in fact, even only a subset of these are involved. These objects that I showed you a minute ago, these capacitance and inductance matrices, are given by some, well, fantastically ugly formulas, but which are completely general. That is, they're purely graph theoretical. And the only thing maybe I would feature about them is they involve both sort of component value matrices involving inductances on the network, but also purely topological graph theoretic matrices, which are just zeros and ones, which give information about, given a certain loop and given a certain branch, in other words, a two-terminal branch, whether that branch is in the loop or not in the loop, or if in the loop flowing in the same direction as the current in the loop or in the opposite direction as that loop. So there's a whole graph theoretic prescription. We actually have Python code that will do all this graphically so that one doesn't have to go to the trouble of computing a lot of ones and minus ones and making a lot of mistakes, which is the way we did it in the first few years. So there's a more or less automated procedure, in fact, that will take an electric circuit and will find a tree for you, compute these topological matrices, these so-called fundamental loop matrices, do all the solve all the linear equations, basically, that will give the effective component values of the Hamiltonian, and also of the master equation coefficients that are needed, at least for estimating T1. Notice I've been saying T1 all along. I never had said T2 because we generally feel that, well, resistors do contribute to T2, but they usually don't contribute sort of in the most important physical way. Usually there are other physical processes that are not especially captured by the circuit model that really describe the processes that contribute directly to T2. Of course, T1 puts a limit on T2. Energy loss puts a limit on how coherent a system can be. So I think I don't feel I'm going to go any further because I don't have any further small chunks to tell you about. This is still, in a sense, work in progress. That I mean, we built a big theoretical structure, and we've, in fact, have not really applied it so much to real qubits. But my intention is to indeed do some of that. One can also go to a sort of multi-terminal version of this, or so-called multi-port version of this. Suppose you have multiple qubits. So in fact, I'll draw it this way. So a multiple qubit circuit in this superconducting world can also be thought of this way, that if you're using these one-junction qubits like transmons, and you have a 4-transmon structure, with some resonators, it still follows this basic schema. That is, that there are branches. Of course, there are Josephson Junction branches, but they're all connected with now a multi-port black box, which is again linear and passive. And but now what I've been telling you is just a one-port Foster analysis. I'm sorry, one-port Brun analysis, so one might wonder, is there a multi-port version? Something that you could adapt to use again rigorously for a multi-port setting. And so I wanted to go back and tell you that the answer is yes, as of the last few months, although again involved us understanding what was really in the electric literature, but not from 80 years ago, but more like 20 or 30 years ago. And so in fact there are It's just one example. So in fact, we do know how to do Brun for multiports. They involve a more extended idea of what a transformer is, first of all. But this is a more or less explicit way that you would do a two-port case. So it involves some complicated or interesting, I might say, transformer structure, which we know how to deal with in our graph theory. And then, indeed, an inductor and a capacitor. Where's the resistor? The resistor is here. So it actually says that the inner essential elements still are, individual LC pairs with one resistor, but with more complicated coupling structures. And so we think that we can do this problem as well, although we've actually not rolled it out for any specific application at the moment. But we are, in fact, intending to work with groups that are developing multi-qubit circuits and seeing what we can make of them with our, rather rigorous way of approaching the modeling. So I think I'll stop now. So we now have a break. I mean, of course, I'm happy to answer questions about this lecture or about the school in general, about the Idea League, anything you'd like. But otherwise, you're free until the presentation workshop and pizza tonight. So.